All right. My name is Dipika, and I, along with my colleague Kyle, will be talking about model optimization, specifically with LLM Compressor, which is a project that him and I work on along with our team at Red Hat. Next slide. So over the last 70 years or so, there's essentially been an exponential growth in the number of parameters within notable AI systems. And although there was essentially a steady increase for the first 50 years or so, since basically the early 2000s, we've seen an exponential rise, first with the development and progress towards CNNs, and then with LLMs in the last 10 years. Slide. And so with the increasing model sizes that we've seen over the last decade or so, there's been essentially a corresponding change or increase in the overall memory that's required to both store and serve these models for inference. But what has not been able to keep up includes the hardware that's available to serve these models, such as the GPUs. For example, one of the latest NVIDIA GPUs includes the B200, which has a memory of 192 gigabytes. And so we need efficient algorithms and systems to help bridge the gap between these models and the hardware that's available to serve them. Next slide. And so what are some of the challenges of AI at this scale, at these large sizes that we're seeing essentially today? The first and most basic kind of cost that we see is towards GPUs and the infrastructure that's required to maintain and run them. And so that includes just a basic financial cost, as well as the cost that comes with just availability and getting access to these GPUs. And then with that, as we get to these kind of larger GPU systems with their larger infrastructure, there's essentially an increase in cost that comes with the energy, as we require increased power consumption to help to run these models. Run these GPUs, especially when getting into the multi-GPU and multi-node scenario. On the other hand, there generally can be trade-offs that come with the user experience when working with these larger models, potentially a cost when it comes to latency and the overall throughput that we're able to get with the model. And as the models have increasing context length sizes, we can also see a potential increase in the model memory that's required for the KV cache in order to maintain that, in order to serve this type of KV cache during inference time. And generally speaking, with these larger models, there just comes essentially a day-to-day cost that comes with making sure the performance and overall accuracy is maintained kind of on a day-to-day basis with these larger engineering systems. Next slide. And so how can AI providers address kind of the risks that we just outlined and the costs of AI at this scale? And that's where model optimization, specifically quantization and sparsification, comes in. Next slide. So quantization refers to reducing the model memory by representing the weights and activations, in other words, the model's inputs and outputs, using a lower bit representation, such as int 8. This allows the models to use less storage. And essentially what we're trying to do when we quantize is essentially identify a scale and 0 point, which when applied to the model, kind of in model weights in this way, were in their new lower bit precision, such as int 8 or FP8. Sparsification or pruning essentially refers to certain model weight values being zeroed out. And this can be done in a particular pattern, such as 2 of 4 sparsity, where 2 out of every 4 values within the model weight tensor are set to 0. And finally, compression refers to saving the model weights in a reduced size without ideally impacting its overall accuracy. And so if we consider one such example of why we should be kind of focused on optimizing these models is if we quantized our model, starting from its bfloat 16 dense precision to its int 8 or FP8, we're essentially reducing, in this example, the model's memory by half. We're starting with a model memory of about 220 gigabytes, which when quantized to int 8 or FP8 goes to about 109, reducing the number of GPUs that are required to serve this model. We can go even one step further and look at int 4 or FP4 quantization, where we're able to reduce the overall model memory by 75% of what it was when it was completely dense in its bfloat 16 precision. Next slide. And so with these quantized models, we're able to see lower latency of our data movement as the quantized weights are able to load a lot faster during inference time. And what we're also able to do is leverage these really high throughput tensor cores. And this is because when we quantize the activations, we're able to apply these matrix operations using with the activations into lower precision. So one such example where we can see something like this is with the H100. GPU. And so in this case, the bfloat 16 tensor core has about 2,000 teraflops. When we compare that to the FP8 and the int 8 cases, the number of teraflops that we have is essentially double than what we get with its bfloat counterpart. And so with that, we're able to get much higher performance by utilizing these tensor cores with both weight and activation quantization. And so generally speaking with that, we're able to use fewer GPU resources, which allow for reduced deployment costs. And overall, we're able to see a decreased latency with higher throughput and able to kind of leverage these larger contexts without issue. And with all of that, we're able to consume less energy and power in order to serve these types of models. Next slide. So here's one example of where we can look at a model, specifically the Llama 370B, in its FP16 precision compared to its FP8 quantized precision. And so the first graph that we're looking at is the overall throughput, and we can see that especially as the number of requests increase per second, the FP8 model is able to have a much larger throughput compared to its dense counterpart, almost exponentially compared to its base model. And then the other thing we can look at is the time and overall latency that it takes to essentially produce the first token. And again, we kind of see a dramatic drop off in overall performance when the model has been quantized. Compared to the model when it's been compared to its dense counterpart than when it was initially quantized. And so with that, we're able to highlight some of the, I guess, one of the key improvements that you're able to get comparing a quantized model compared to its dense counterpart. Next slide. And so one kind of key question that comes up when we consider model optimization is what happens to the memory. Is what happens to the performance. Generally speaking, with larger models, we're able to see better accuracy, and this is something that's been very common kind of over time. Generally speaking, like larger models are able to perform better and able to be just better at generation and overall skill in terms of when we look at them in terms of their accuracy. However, with quantization, we're able to see fairly consistent performance compared to when we compare the quantized models with their dense counterparts. But this is not always the case. Next slide. And it's not a perfect match. And this is what in one such example where we see this, where we compare a dense model, specifically the Qwen 14B, and its quantized int4 counterpart. And we can see that the overall performance, there is a slight drop off. However, next slide. This is not always the case, and we can actually sometimes see that quantization actually helps with the overall accuracy of the model. And in this case, specifically, the Qwen 14B does a little bit better when it's quantized to FP8 compared to when it was in its FP16. Next slide. And now I'll have Kyle take over.
Cool, thanks, Dipika. So as Dipika kind of mentioned, quantization and model compression in general is a really powerful technique for taking models and being able to deploy them with really high throughput and low latency. However, so that's kind of where LLM Compressor steps in. So LLM Compressor is a product developed by Neural Magic and now Red Hat AI, which is an open source framework for allowing you to apply state-of-the-art research algorithms to optimize your models for inference within vLLM. So LLM Compressor is a tool that kind of sits in the middle between having your base model, which is unquantized, and trying to deploy that model within vLLM in a performant way. LLM Compressor basically utilizes these algorithms and saves that compressed and optimized model in the compressed tensors format for serving in vLLM. So how do you get started with LLM Compressor and using these techniques? Well, we'll go through the 4 steps that are required to figure out how you want to quantize and optimize your model. And then at the end here, we'll talk about like an example of going through how to actually do it using a specific code. So the first step here is choosing your model and dataset. This is pretty straightforward, where you come to LLM Compressor with a model and perhaps a use case in mind. And then LLM Compressor handles the quantization. So in this example, we can use something like a Llama 8B model, and then also choosing a dataset to use to calibrate this model. A dataset isn't always required, but it's often useful for things like activation quantization and improved weight quantization, which we'll get into more later. The choice of dataset doesn't really matter too much. Most cases, you'll be able to get away using the UltraChat dataset, which is a very general dataset used for calibration. Unlike fine-tuning, the dataset doesn't actually have to reflect the actual distribution that your model is using, but using a dataset that does reflect that distribution can yield benefits. So once you have your model and your dataset, you can load these directly in transformers and then call the one-shot function, which is provided by LLM Compressor in order to compress your model. So for example, we're compressing a model using the UltraChat dataset here. If you have your own custom dataset, as I mentioned previously, you can load that directly using the Hugging Face datasets library. and then pass that into the one-shot function in favor of the pre-baked kind of data sets. So next, once you've had your model, we can choose a scheme. So quantization schemes are basically the configuration that specifies how quantization should be applied to your model. Each of the different quantization schemes comes with different benefits and downsides. So for example, weight-only quantization, W4A16, meaning weights are quantized to int4. That obviously yields much better memory usage because each weight, rather than having 16 bytes, as in the bfloat16 data type, we use int4. So each one only uses 4 bits. And I meant to say 16 bits previously. So going from 16 bits to 4 bits is a huge decrease in VRAM usage. And you're able to leverage the Marlin kernels on vLLM using any kind of GPU that's beyond Ampere. This table shows the other kinds of schemes that are available. So, int8, FP8, and then most recently with the Blackwell GPUs and VFP4 data types. All of these kind of have upsides and downsides, and there's more information on the LLM Compressor docs page where you can look through. Moving on here, you can also apply different strategies when quantizing your models. So once you've chosen your scheme, you can choose a strategy, which basically means what kind of granularity is the quantization being applied to. Higher granularities means that you're going to have better accuracy recovery, but you're going to have slightly more inference time cost. All of these are kind of displayed here, and all of these are available within the LLM Compressor framework for you to use. The most common quantization strategy is group quantization, but we're most recently adding support for things like block quantization, which was most recently used within the DeepSeek models, and it's been proven to be very powerful with FP8. Cool. Obviously, there's a lot of different configurations you can use, but just to summarize at a high level here, if you want to optimize for things like latency or VRAM usage, use a quantization scheme, something like W4A16, because that's going to take your 16-bit weights and quantize them to just 4 bits, which is a great reduction in VRAM usage. If you're optimizing for something like latency or throughput, so more high volume requests, quantization schemes like int8 or FP8 are going to be a lot more suitable because you're going to be able to leverage those high throughput tensor cores on the GPUs, as Dipika mentioned earlier. Cool. So now that you've chosen your model, your data set, and then also chosen a scheme, basically kind of the way you want to optimize your model, now you choose an algorithm with which to apply that scheme. All the algorithms available on LLM Compressor can basically be grouped up into 4 types. There's the weight and activations group algorithm. So that's kind of this round to nearest quantization, which we'll talk about in the next slide. For improving the accuracy of weight quantization, we can use something called GPDQ or AWQ, which are more advanced algorithms which improve the accuracy recovery of weight-only quantization. In addition, we have some other kinds of techniques here. So things like sparsity can be applied using the sparse GBT algorithm. And then things like transforms and smoothing can help improve the accuracy recovery even further beyond what even round to nearest can provide. So we'll go through all of the algorithms really quick just so you can get a taste of what is available within LLM Compressor and all of the really great research that's available. So the quantization modifier is the basically the class that you're going to be using if you want to apply round to nearest quantization to your model. This is the most kind of standard and naive way of quantizing a model, where you just take the weights and activations and kind of round them to their nearest values within the quantized space. This is most straightforward, and it also allows you to apply things like KV cache quantization, which can help reduce your KV cache size and allow you to have much larger context windows during inference time. If you want to improve upon the round to nearest quantization, you can use something called GPDQ modifier. This modifier was, or this algorithm was developed by Dan Alstra, as well as in collaboration with Neural Magic. And this algorithm is a little bit more involved than the round to nearest quantization, but yields much better accuracy recovery. This technique basically computes a second order differential against all of the weights being quantized, and then optimally chooses the order in which weights should be quantized, and then propagates the error of that quantization to all of the other weights. As I mentioned before, this GPTQ algorithm can be used using the GPTQ modifier, which you include within your recipe when compressing with LLM Compressor. We have lots of different options, so things like choosing the block size, which chooses like the granularity of those optimization backpropagation steps. Things like the dampening fraction, which kind of controls the aggressiveness of the algorithm as opposed to kind of like defaulting to round to nearest like properties. And then things like activation ordering can also really help improve accuracy recovery. Cool. Moving on to your AWQ modifier, also an algorithm targeting weight-only quantization. The basic idea here is that if we look at a model architecture and we look at all of the layers that happen after layer norms, we realize that there is a property here where if we apply a scaling factor to the norms and then a scaling factor to the layers that happen after those norms, we're basically able to migrate a lot of the outlier quantization difficulty of quantizing weights and moving that, of quantizing the activations and moving them to the weights, which can make weight quantization much easier to apply. This is implemented here as well. This algorithm in particular is particularly memory intensive and then also computationally intensive, but does yield much better accuracy recovery. So something to keep in mind if you end up using it in your recipes. Moving on to sparsity here. So sparsity can be applied using something called the sparse GPT modifier. This algorithm is very similar to GPTQ in that it's almost the same exact algorithm where you basically apply your sparsity and then compute the error with respect to that sparsity and kind of propagate that out to the rest of the weight. This kind of sparsity is very useful for things like 2-4 sparsity, which Dipika mentioned earlier. And 2-4 sparsity is a special kind of sparsity structure, which can be accelerated using specialized GPU hardware. Moving on here, we move to the algorithms which help assist round to nearest quantization and improve their accuracy. So things like the smooth quant modifier is very useful for kind of similar to AWQ, kind of migrating quantization difficulty from norms to weights and vice versa, and particularly useful for FP8. Finally, we get to our most complicated and most recent addition to our algorithm kind of repertoire here, and that is transforms. Transforms is this technique where you add additional layers into the model, and these additional layers have this property where they are, as you say, like they are orthogonal matrices. And what that means is that if you apply this matrix once and then you apply the matrix again, those two applies cancel each other out and create an identity. And with the added benefit of these transforms is that they actually modify the distribution of the weights and activations to be more normal and easier to quantize. This is described more in the paper as well. So if you're interested, you can take a look at that. And then also within the latest LLM compressor edition of the vLLM office hours, we also explain this in more detail as well. These algorithms can be applied using the quip modifier to apply them in a kind of similar style as the quip paper describes. And then the spin quant modifier, which applies them in this kind of like more complex scheme where you apply transforms to different layers and these layers kind of cancel each other out. So it means that you basically induce no runtime cost. Cool. So those are like a very, very broad set of like all of the algorithms available with LLM Compressor. Just to simplify all of that for you, if you want something that's really fast and simple to just kind of get out the door in terms of optimizing your models, use something like the round to nearest quantization, which is implemented by the quantization modifier. If you want something with better accuracy recovery, especially with weight-only quantization, use something like GPTQ or AWQ. Those algorithms are a little bit more intense and might require more VRAM requirements during compression time, but they're going to yield much better accuracy recovery once loaded within vLLM. If you're interested in things like 2-4 sparsity for better throughput, SparseGPT is a great way to kind of sparsify your model. And then if you're interested in more experimental results and in more experimental techniques, use something like transforms with GPTQ, which can help boost accuracy recovery even greater, or in cases where standard GPTQ or AWQ doesn't yield the accuracy recovery that you want. Cool. We finally move on to step 4, which is the easiest one, which is simply saving your model and then loading it within vLLM. When models are saved, they're saved within this kind of quantized checkpoint format. So you might notice that your model has been modified with extra parameters. These are things like the weight scale and 0 point, and then same thing for the activations input scale and input 0 point. These scales and 0 points are what is used to quantize the models during runtime. And although they induce a little bit more runtime cost, they're what's enable the quantization in the first place. Finally, this quantized checkpoint is saved within the compressed tensors format. This format is an extension of safe tensors and is loadable directly within vLLM. It also implements a lot of really neat features, like being able to take those models and packing them together into bit packing them into bytes, which makes for the loading both like saving the model on disk is smaller, and then loading it within vLLM is much faster because they're in that packed format. The compressed tensors format also comes along with a config, which kind of specifies exactly how you applied quantization, which strategies you used, and which schemes you were using. And all of this information is necessary to load within vLLM. But luckily, you don't have to handle any of that, because loading in vLLM is very, very simple. You just simply pass in your model's model path, and vLLM handles all of the loading of the compressed tensors format. And then also the selection of quantized kernels, which help accelerate the model inference. So that was a kind of really high level view of how to use LLM Compressor. As I say, like all of these, there are lots of examples within the examples folder within the repo that you can take a look at. Over the development of LLM Compressor, we've added a lot of support for different flows. So things like multimodal models, MOE models, very large models, being able to load within just one GPU using sequential onloading. And then more support for things like KV cache and attention quantization are things we're developing as well. So if you're interested in taking a look at LLM Compressor, start with some of the examples and start quantizing some of your models on your own. And then from here, I'm going to pass over to Dipika, and she's going to talk through one of the examples, or 2 examples, of how to use LLM Compressor using real code.
Awesome. Thanks, Kyle. Can you go to the next slide? So one example that we have is the FP8 dynamic per token quantization, which is a data-free pathway within LLM Compressor, and probably one of the most popular pathways within that is often used for model generation. So here we load the model kind of like you would normally using the Transformers auto model for causal LLM library. And specifically, we're targeting the model stub, the DeepSeek R1 Distill Llama 8B model. And once loaded, what we see here is something called a recipe that essentially uses kind of like what Kyle described as the quantization modifier, and also specifies what layers we're targeting for quantization. So in this case, all the linear layers are being quantized. And specifically, we're applying an FP8 dynamic quantization, which means that all the weights that are in the linear layers will be quantized to FP8, whereas all the activations will be dynamically quantized during runtime. We specify and provide that recipe along with that model to our one-shot API, which is the main entry point and API for quantization within LLM Compressor. And at the end, we save that final model, which, next slide, is saved to disk, and it's quantized, compressed, and ready to run in vLLM. Next slide. We can look at another more complicated example, specifically with NVFP4 quantization. So NVFP4 is NVIDIA's FP4 format for quantization. And here we start like we did before, in the sense that we define our model and we load it using the Transformers primitives. However, we have to additionally define some data that we can use to quantize and calibrate our model. And this is in order to help calibrate some of the quantization scales to make sure they're optimal. And so in this case, we define the Hugging Face Ultra Chat as the data set that we're going to use, as well as the number of samples that we want to use, which in this case is 20, as well as the max length sequence length, which is 2048. Next slide. We then define some of the steps to process the model, such as loading it, applying its chat template, and then as well as what the tokenization will look like. LLM Compressor has some support for out-of-the-box data processing that you can look into, but if you can definitely you can definitely set up your own data set and use it as well. And this is just kind of one such example of on what type of processing that it would involve. Next slide. And then just like before, we define our recipe, which again specifies the layers that we're targeting, which are again our linear layers, the scheme that we're using, which is NVFP4. And in this case, we're saying we're ignoring quantizing the LM head. And finally, we again call one shot, defining the model, the recipe with the data set, as well as the number of calibration samples and max sequence length that we had defined before. And finally, one shot will produce a model that's quantized, which again will be saved, compressed, and ready to run in vLLM. Next slide. So you can definitely try some of the examples, and if you are interested, our research team has worked with us to quantize a ton of the models that are very popular, such as the Llama 4 Herd, DeepSeek, as well as some of the vision language models, such as Qwen 2.5, and more recently the Qwen 3 vLLM models, and all of them are available on the Hugging Face Hub with evals for you to use. Next slide. And just to kind of summarize, LLM Compressor is, there's something for kind of anyone that's trying to optimize their models for inference. For practitioners, there's a ton of off-the-shelf validated models that they can use, as I mentioned on the Red Hat AI Hub. For developers, there's easy-to-use recipes with a lot of configs that we have set up to make sure they work well with the vLLM. And for researchers who are looking to have just a little bit more control on how the model is actually getting quantized, you can go through LLM Compressor and make those changes. And we're available on like the vLLM Slack as well to help you kind of guide through some of the changes that you're looking to make. Next slide. So where do you get started? Again, LLM Compressor is just a pip install away, and you can definitely open up any questions or thoughts that you have. Again, as I mentioned on the vLLM Slack, or opening up some sort of issues, like using first good issues. Definitely get involved, ask questions, and we're happy to help kind of anywhere we can there. Next slide. And just to kind of just to summarize a little bit about Red Hat with LLM Compressor. LLM Compressor is part of the Ray's Red Hat AI Inference Server image, and every kind of release that they have, LLM Compressor is part of the model opt image in that, and so it will be GA and when the release for 3.2.3 comes out later this month. And next slide. This is just, we can just skip through this, just giving you a little bit of a kind of overall with highlights. We've talked about a lot of these today, but this just summarizes some of the new things that are coming up and coming with LLM Compressor. And we also do blogs on every sort of release that kind of highlight a lot of this. So you can definitely check those out as well. Next slide. And thank you. And thank you for joining us today. And we hope to see you on the issues in vLLM page.